Hello, and welcome. We're nearly at the end now. We've just got the two. So, including this one, we've just got 3 more chapters to do. So, this and then, which is not that bad. So, 3 more chapters. So, this one is another long one. Well, sort of long. This is all about Newton's laws of motion. Now, the first law of motion that Newton created wasn't just, oh, an apple fell on my head and I said gravity. It wasn't that. The first one that Newton came up with, or Newton's first law, is, I'm not actually going to write it down because I need space for later, but a body will remain either, I won't write it down. A body will remain either at rest or in equilibrium, or say equilibrium constant velocity, if all forces are equal and opposite to each other. So this means this could be used in the context of, say, terminal velocity. So you could quote Newton's first law as why an object appears to be in terminal velocity. The second rule is force equals mass times acceleration, which is the big one, which can be used in hills, it can be used, inclined planes, it can be used in lifts, try to think of what they were called then. Yeah, so lifts, and they can be used in pulleys as well. Oh yeah, rockets as well, sorry, I forgot about that. So, as we said before, we're going to concentrate on Newton's second law. The other two are... the third law is Newton said that if a body is acted on a force, the other force will have an equal and opposite reaction force. So, for example, if I try to push a big building, I'm going to push back on the floor as I push towards a building. And obviously the building falls over, and that's what happens when I push a building over. Don't know about you. But anyway, so that is Newton's third law, but they don't ask you. It's generally about the first two, if I've got that. They're 3 laws. I'm fairly sure that first is the equilibrium, second is the force equals mass times acceleration, and hopefully the third one is the equal and opposite forces. So, what we're going to concentrate on today, as I said, is force... I really need to get any pens. Force equals mass times acceleration. Force equals ma. Now, that is a basic formula, and I don't like basic stuff. So, force equals mass times acceleration. So the force is not just a force, it's the resultant force on a body. So, if the resultant force is 0, then it's in equilibrium, as Newton's first law said. So that's why they all follow each other, and that's what's quite nice about them. Obviously, they had a go at each other, and didn't like each other, and would have a problem. But they don't, so that's okay. So, as I said, the resultant force equals mass times acceleration. And you can put that into any situation, but I'm not going to because I don't want to waste your time. Hopefully, you do understand where I've come from there. Because if a car accelerates, you're going to have resultant force backwards. Well, the resultant force is forwards actually, but you feel it going backwards, if you can imagine that. Yeah, so force equals mass times acceleration. And we can put this in the context of the first one we're going to do actually. I'm going to do the sorry, let me just doing the car one first. Okay, so we've got a car here. So it's why I didn't take art. And then we've got a trailer. Now, they are going to experience exactly the same interaction, acceleration even, otherwise the car would shoot off and we'd say goodbye car, or the trailer would go, I'm leaving your car, and it'd be a big argument and then people die, and very good. So, what we were saying before, force equals mass times acceleration. So the acceleration is the same for both the car and the trailer. Sorry about that, guys. Now, I'm not sure if I explained this before, but F is the resultant force on the car and T is the resultant force on the tow bar of the trailer. So, we can, yeah, on the trailer. So the, so there is, yeah, the trailer. So the resultant force between the trailer and the, sorry, T is for tow bar even. So the resultant force on the tow bar is, you have to take away that from the force of, resultant force of the car. So F take T equals A. Now the M is, so yeah, so that becomes, if you want to work out T equals F take MA. Big M is for the car, so the big M could equal 1,200 kg. It's probably quite light, and M could equal 300 kg. So that would be T. I'm not going to put any values, I'm just going to show you what big M means. 1,200 times A. So that's the resultant force on the tow bar. So F is resultant force on the car, T is resultant force on the tow bar, and that is resultant force on the tow bar. Now the engine force is the big mass, so the engine is pulling the whole thing along. So, as F equals MA, the mass is the big mass of the car and the trailer. So, M equals big M plus little m. So it's 1,200 plus 300, 1,200 plus 300, that's kilograms, times A, and that will give you the force of the engine, which is F there. So just to recap that bit, the bigger force, take away the tension in the tow bar, is equal to the mass times the acceleration of the big car. Yeah, it's definitely 200, yeah. And the big resultant force in the car is equal to the whole mass times the acceleration of the objects. Now that's quite simple for the car and the trailer scenario. So force, take the tension in the tow bar, or the tension equals mass times acceleration, and you could just move the effort across to get T equals force, take away mass times acceleration to get the tension in the tow bar, and then the big resultant force in the car is mass times acceleration, and that is the big mass of the car and the tow bar as one. So hopefully I'll give you a minute to pause the video now, and you can go over it, and there we go. So hopefully you paused it and noted that down. So that is the car analogy there. Right, sorry about that. So, the next thing we're going to look at is the rocket. So I know this doesn't look like a rocket, but for funny purposes I'm drawing a square. That's my rocket, that. So for it to go up, T equals mg plus ma. That is just a formula you need to know. I'm not sure if you can see that. You should be able to now. Zoom it in a bit for you. Yep, hopefully you can see that. So that is T equals mg plus ma. That's your rocket. That's a minimum vertical thrust it needs to go up by. Yeah. So that's the formula we're going to use for the next thing we're going to do. Well, the next thing we're going to do is a lift. Now, a lift... So, yeah, you've got a lift here. You get the weight of the occupants dragging it down, and the tension in the rope pulling it upwards. So you've got the T, and you've got the W. And that is basically, I'll get rid of the rocket now. That T, instead of becoming the thrust, that becomes the tension in the rope. A second. Well, right. So that becomes tension in the rope. And now that is either bigger or smaller than mg. And this would indicate either Ma positive or Ma is negative. Now, how do we work that out? Well, my dear friends, if you can imagine the acceleration is going upwards, so even if it's going down and accelerating, to mess up your mind, that's going down and decelerating. So the overall movement, if you can think of it as going down, is, even if it's accelerating downwards, is actually decelerating because the T, the weight, is less than the tension. So the tension is being pulled down, so the tension is less than the weight if it's being pulled down and stopping. Yeah, and increasing even in speed. And then we've got the other arrow, so this could be one arrow, and the other arrow is the movement up or down. Now, this is the way I think of it. If you've got a different way, obviously use that if it works for you. But the way I look at it is this. So if these two arrows, so if the acceleration and the deceleration, remember acceleration, in my view, the way I'm going through it, if it's going upwards, if it's accelerating, the acceleration arrow is pointing upwards because the tension is upwards, so it's pulling it upwards, the overall force is upwards. However, if it's being pulled downwards and accelerating downwards, then it's being pulled downwards by a greater force, so it's the tension is being pulled down, so it's decelerating from the upwards force. That is the first arrow. And then the second arrow is just the way it's moving, so it could be moving up and decelerating. That is irrespective of the second arrow. However, if the first arrow and the second arrow, so if it's going up and accelerating, or if it's going down and decelerating, then the tension is larger than the weight because the overall force is being pulled upwards. So if it was originally accelerating downwards, then it's going to be being pulled upwards to slow it down. So that is a positive, because that means the tension is larger than the weight, and the weight is mg. So if the tension is larger than the weight, we can say T equals mg plus ma, and it's going to be larger than mg, so A is going to be larger than 0. However, if they are not the same, so if you've got it going up and decelerating, then the overall force is being pulled down because it's going up, but it's slowly going up less each second. So that means the weight is pulling it down greater than the tension is pulling it up. So that means the acceleration is going to be less than 0. So that means it's going to be negative. So T equals mg take ma. So it's going to be less than mg. Hopefully you've got that. So mg is the weight downwards and T is the upwards. So you've got to work it out in your mind. If that arrow thing confused you, I'm going to try and explain it in a simpler way. So, if you can imagine, the resultant force is the way the lift wants to go, and if it wants to go upwards, well, obviously it doesn't have a mind of its own, but I'm just trying to get it through to you. So, if the tension is larger than the weight, then the overall force, if it carried on, would end up going upwards. So, to give you an example, if it's going downwards and decelerating, you think, well, it's going downwards, isn't it? Well, it's not. As I said before, 2 arrows point. No, forget the arrows actually. Yeah, so it's going downwards, but it's slowing down. That means the overall force is larger, being pulled upwards. So when it gets to a certain point, after going so many meters, the eventual outcome will start to go back up, then keep on going back up, and then start accelerating upwards. So we'll get the same effect as if we started with it going upwards and accelerating, as the tension is immediately greater than the weight, as it is for the other one, but it becomes more apparent that it is. However, this is the other way round, then the weight is larger than the tension. So if it's going up but decelerating, it was originally being pulled up as a larger force, so the tension was originally larger, but as it's slowing down, as it's going upwards and slowing down, then the force pulling it down is larger. However, if it's going down and being pulled, if it's going down and being pulled, going down, so hopefully that's helped you to understand it. Yeah, so the 2 arrows there are the opposite, then it is A is less than 0, however if the same, so up and accelerating or down and decelerating, then the A is going to be larger than 0, or the other way around if it is the other way around. I'm really sorry if you can't get that, but that's just something you're going to have to know. It's quite confusing, I know, that's why I've tried to spend a bit of time going over it. But again, you can re-watch that bit of the clip, and it is quite hard, that. Honestly, that's probably one of the hardest things you have to understand, not so much the physics, but just to get your head around what's going on. And then we have an inclined plane. If you're watching this the right way around from the physics videos, or if you're watching this the right way around through the course, then you would have already seen a slope and know what parallel and what the forces are perpendicular to this slope. So I'm just going to assume you know that for this section. So parallel, you should know, is mg sine theta. Now, the way I think of it, without explaining in terms of mathematical terms, I just think if it's going up the slope, it's sine, because you can imagine always sine going the up bit of the triangle. So it's always going up the slope. I mean, it's not always the up bit of the triangle, but it's always going up the slope. That's sine. It's going up. However, cos, it's perpendicular. So the only other one, apart from sine, is cos. So if you can remember sine going up, use cos for the perpendicular. So, with resolving forces, find out the mass. Mass times acceleration, resultant force. So, the resultant force, upwards and downwards force on a slope, we assume to be equal. So the 2 forces are the normal force and the cos force, the mg cos. And if these were different, then we know they're the same, because if they were different, then it'd end up flying off if the normal reaction force was larger, or sinking into the slope if the mg cos force was larger. So let's assume they're equal. So we don't have to resolve them, they're already resolved, and the answer is 0. So you can virtually forget about these forces for AS. Well, you can virtually forget about them anyway. So, they're the two forces that we've sorted, and I've hopefully explained why you don't need to go over them forces. So, how can we relate this to Newton's laws of motion? Because it is, in essence, part of this force equals mass times acceleration. So, let's go straight from the beginning. Force equals mass times acceleration. Now you should know F is equal to the resultant force. So the resultant force, as we said, of up and down is 0. So the two resultant forces we need to do is up the slope and down the slope. Now, parallel means just along the slope. So mg sine is along the slope. I know I said up the slope, but it depends which way the object is moving. I just said up to explain my point why I use sine. So this is mg sine theta. And that's going to act down the slope. Now, there's a couple of conditions here. Generally, you have Fr. Fr is the resistance force. Sometimes you even have something called Fe. You may go, well, what's Fe? Well, Fe is the engine force or the motive force of the object. So you just cancel them out. You work out mg sine theta, which we've done, and add Fe and take away Fr. So that's the resultant force. But how do we put that into the equation? Well, we simply substitute it for F. So, as we said before, mg sine theta plus the engine or motive force take away the resistance force. Now the resistance force is the sum of the individual forces that oppose motion. Generally it is friction. That is generally what they'll ask you about in the exam. Quite general that. So mg sine theta plus Fe take Fr equals ma. Normally they give you the mass, otherwise you won't be able to work out mg for the sine theta bit. And you just simply, if you wanted to work out a, then I'm not going to resolve the top bit. Mg sine theta plus Fe take Fr over m equals a. That is the inclined plane bit of physics done. Now, if you're a person who doesn't take advanced mathematics, then well done, you've just done, that is a mechanics question for an advanced mathematics paper. In mechanics, anyway. So, you can feel pretty darn good about yourself for that one, because that is on an advanced paper, that. And physics is quite advanced, but, you know, hopefully I taught that quite well. But generally, though, I mean, they don't give you a motive force. So you just, for anything, you just put Fe is equal to 0, or you can just leave Fe out of the equation without adding anything at all. Sometimes they don't even give you a resistance force, they just give you mg sine theta. Well, they just give you the angle. That's all they need to do. And I don't think mg sine theta is given as a formula in the exam. So that's pretty much all there is to Newton's laws of motion. Obviously, if you want to look at the other two, you can check it out on the science labs, or I recommend the student room. It's a good site I've used over the years. And I'll hope you enjoyed that video, and we'll see you in the next one.